hello everyone. Welcome to my talk. Indeed, I'm going to talk about the Atlantic meridional overturning circulation and its role and its role in climate change and how climate change affects the Atlantic meridional overturning circulation. So first of all, let me, all right, just one more thing. Okay, this works. All right, first of all, let me thank my collaborators. They all collaborate on this project, ARChange or ARChange, a numerical modeling of Arctic climate change, global ocean circulation, and basin interconnections. And this is a pretty big group of people. First of all, people at Lausanne, at the lab in Paris I'm working in, including Eric Guardi, Juliette Minot, Ioania Pove-Perez, our postdoc Brady Festa, and Amelie Simon. And then a number of USA collaborators, my former students and postdocs, and my current students and postdocs. I'm not going to name everyone, but you can see them here in this slides. And actually, over the years, some of them got faculty positions and staff positions in various places. And so I'm indebted for their work and contribution, not just to this project, but for many papers and projects we put together, we worked on together. All right, so the Atlantic meridional overturning circulation. What is the AMOC? So if you go back like 10, 20 years from now, people would say, well, the thermohaline circulation. Now the most common term used is AMOC, so the Atlantic meridional overturning circulation. And if you look at a schematic of general ocean circulation, what you'll notice, the Atlantic plays a very important role, and that's because deep water is formed in the Atlantic. So cold, dense waters, they sink in high latitudes in the Atlantic, in the region around Greenland, in the Nordic seas, and they fill the ocean. There are other regions of sinking of dense water off the coast of Antarctica, but the ones in the northern high latitudes in the Atlantic are responsible for what people sometimes call the ocean conveyor belt, or the ocean heat conveyor belt, whatever term you would like to use. So if you focus on the Atlantic, this is the circulation you would have in some very schematic way. It's a complicated three-dimensional circulation, and this cartoon obviously is much too simple, but it does show this red route with waters going from the south to the north. So these are warm surface waters. They sink in high latitudes, and they fill the ocean with blue routes. So it's deep at depths of 2,000, 3,000 or so meters. So sinking requires to have dense water. That means a relatively cold water and relatively saline water. So the fact that part of the circulation includes the Gulf Stream is important because the Gulf Stream brings relatively saline waters from the subtropics to high latitudes. In high latitudes, that gets cold, they get colder, and so that's where this dense water is formed. And so you have this conveyor belt. So the Gulf Stream is an important part of AMOC, but it's not the only part. Again, it's a complicated three-dimensional circulation. And the Gulf Stream itself is driven by a combination of forces, including winds, including the temperature and salinity contrast in the ocean. So even if the AMOC collapses for whatever reasons, the Gulf Stream will continue flowing in the Atlantic, even though perhaps in a weaker shape or form. And so this is a sort of schematic way to look at the AMOC. And typically, the actual AMOC, when people try to use this word in a strict sense, it's this overturning. So it's a zonally average circulation with surface waters traveling from low latitudes near the surface to high latitudes in the Atlantic, where they sink and then they fill the entire ocean. So this is this overturning circulation in the AMOC name. And this is a stream function from an ocean model showing this overturning. So the strength of AMOC is estimated at about 17 times 10 to the 6 meter cubed per second, or as oceanographers use the term Sverdrup, so 17 Sverdrups, plus or minus a few Sverdrups, plus there is variability on top of that. But give or take 17 Sverdrups is a good measure of this overturning circulation. It's 2 orders of magnitude greater than the transport of water by the Amazon, for example. So it's a lot of water. It's relatively warm water, and so this circulation brings a lot of heat to northern high latitudes and affects sea surface temperatures, and this is why it's important for climate. All right, so over the past 10 years, we have this intense debate whether the AMOC is weakening. And this debate continues, and I just give you these 2 papers, recent papers. So one saying that current AMOC is weakest in the last millennium, during the last century. And then a paper from a few weeks ago saying, well, natural variability has dominated AMOC for the 20th century. And basically, the first paper claims that the AMOC is already weakening, and the second saying whatever we see in this weakening is actually whatever natural variability you expect from AMOC. And you can see from the figures, these are sort of temperature anomalies that people try to associate with AMOC. And in one picture, it's going down. In the other picture, it's just going up and down. But the questions of whether the AMOC is already weakening and how much is going to weaken with global warming is obviously an important one. And just to emphasize how difficult this question is for the present time, this idea that has been around for a while, that the so-called observed North Atlantic warming hole is a potential evidence for the AMOC slowdown. So the warming hole, so what you see is here, these are trends for the past, say, 70, 80 years. So you see warming almost everywhere, but in the North Atlantic, there is this blob. Some people called it the cold blob. Some people just say in the North Atlantic warming hole. It's apparent in different data sets. In some data sets, it's just suppressed warming. In some data sets, it's actually a cooling trend, 10th of a degree per decade. And it is climatically important. And people will try to explain it as well. The AMOC is slowing down already, so it would bring less heat to high Northern Atlantic, to the high latitudes of the North Atlantic, and you will see it as this warming hole. And many proxies that use this idea that AMOC is slowing down, one way or another, are using the idea of temperature as a proxy for AMOC. This is the North Atlantic warming hole is one of them, but there are other indirect proxies. Well, the problem is if you look at the trends of winds over the same time frame, and this is in the left panel, you can actually see a strengthening of winds over this region. And a strengthening of winds would mean higher evaporation. It would also mean more transport of cold water from the north to the south because of the so-called Ekman transport. On rotating planets, if you have zonal winds in the northern hemisphere, they would generate transport of surface waters 90 degrees to the right. So this cold water would move southward. And that would be another explanation for the warming hole that has nothing to do with AMOC. And so it's very hard to disentangle the signal of global warming that affects sea surface temperatures, winds, sea level pressure, and AMOC from a direct effect of AMOC weakening. All right. You obviously want to have direct observation of AMOC, and we do have those, and in particular, there is this nice oceanographic rapid array. Rapid refers to rapid climate change that measures the strength of this overturning at roughly 26 degrees north through a series of mooring stations that measure temperatures, salinity. Some of them would measure velocity, plus the Gulf Stream is flowing through the Strait of Florida, and you measure the transport of the Gulf Stream by underwater cable. So unfortunately, this array has been operational for about 16 years now only. So it's very hard to make conclusions on the strength of AMOC based on such a relatively short time series. But we can still see, and this is the red line here on the top panel, that at least for the time frame of these observations, the AMOC seems to be slowing down by a few Sverdrups. And together there is a reconstruction of AMOC going into several decades in the past, and this is from Fryker-Williams paper. And this is based on satellite measurements of sea level. And so according to this paper, well, you can probably say that the AMOC was weakened at least for the past something like 10, 15 years. The problem, if you look at other reconstructions, and I just bring out this one, and this is from the so-called ocean reanalysis. It's an ocean model with assimilation of data. The red line agrees pretty much with the reconstruction. So it's the same red line as in the top panel. But if you go to the past, this particular ocean reanalysis actually showing weaker AMOC at the beginning of the time series. So while in the first panel, it's a decline in AMOC, in the second panel, it's actually nature of variability of AMOC, where AMOC goes up and down. So you don't really know. And if you look at other papers, it's basically going back and forth. AMOC is declining. Well, no, it's not declining. But I guess this is the state of affairs at the moment. What we are more or less sure now, however, to the extent you can be sure about modeling results, is that the AMOC is going to decline in the future. And this is a very robust result across all the models we have. And this is from IPCC, previous IPCC report. The more recent IPCC report shows exactly the same. Whatever scenario you're using, the AMOC is projected to decline. And the physics is very simple. You are warming surface waters much faster than the deep ocean. This dense water that is supposed to sink is actually getting warmer, while the deep ocean is not getting warmer as fast. So this suppresses sinking, and so the AMOC is going to weaken. The problem is, if you look at different models, they all show different rates of decline. They all show different mean state of AMOC. And some of them actually show even a collapse of AMOC, but not in the 21st century, but if you go to the 22nd century. Obviously, there is a dependence on the scenario, on the rate of decline. But regardless of this, if you choose the same scenario and you look at the rates of the decline, they can vary something like by 50%. And that's important because the AMOC has a very vast climate impacts. You can also use these results to look at what models project for the present, because some of them started earlier. And so this is for the last 20 years. So some models do project a decline of AMOC, a little bit of a decline already. Some models still say, well, it will continue at the same rate for a little while and then start declining. So unfortunately, model projections for the current state of AMOC disagree. Again, they agree about the future, that the AMOC is going to weaken. They disagree on the rate of weakening, and they disagree on what's happening right now. So why do we care about the state of AMOC? Well, there are many things, and here I list just a few. And one you can think about, well, if the AMOC at some point shut down, well, it will disrupt the ocean sink of CO2. Currently, 25, maybe even 30% of CO2 go into the ocean. And in this map, you can see the regions of sinking of CO2 into the ocean. So this is CO2 flux. And high latitudes North Atlantic is one of the regions where there is a lot of CO2 going into the ocean. If AMOC weakens, and especially in the case of shutdown, you prevent sinking of water. And so you can reduce considerably the amount of CO2 going into the ocean in this region. So that's one important thing. And obviously the disruption, not just of CO2, this is a disruption of the entire carbon cycle of the ocean. But then there are impacts on the weather and climate that's quite important as well, direct impacts. So the weakening of AMOC would increase land-sea temperature contrast because it will reduce the heat transport by the ocean. And that would increase storminess in mid-latitudes. Every time you increase land-sea temperature contrast, that can lead to more storms. It will shift tropical cyclones, the distribution of tropical cyclones, reduce precipitation over Europe, shift the Atlantic tropical rain belt southward drying the Sahel, and many other things. And I worked on this second suite of problems, and so I'll talk about them a little bit more. And in particular, we conducted numerical simulations, idealized numerical simulations, running a projection, a global warming projection, and then running another global warming projection where we artificially fix the strength of Emoc. And so this is an example of what we did. So the purple line here, the Emoc strength remains the same. The green line, the Emoc declines, and this is the green line is a part of global warming. So both actually are part of global warming, but in the purple case, we just artificially fix the Emoc strength. And then we can compare the two simulations and look at climatic impacts. And this is what we observe. So the purple and the green line now for global mean temperature. So the green line, so Emoc weakening, produces a little bit less of a global warming. By the end of 21st century, a few tenths of a degree weaker global warming. Well, it's somewhat good news, but there are other things. And in particular, if you look actually at spatial map of the cooling due to the reduction of strength of Emoc, it's concentrated in high latitudes North Atlantic. We get something like -3 degrees C just due to the weakening of Emoc. And again, I should emphasize this is on top of global warming. And global warming gives you like 4 degrees warming globally. So this -3 degrees is a relatively minor signal in terms of global warming. But a contrast of temperature, changing the contrast of temperature by 3 degrees between the ocean and the land, it's quite a significant thing. Well, one thing I should emphasize, well, the day after tomorrow doesn't happen, so Emoc weakens, but the cooling, the general cooling of the ocean and even overall, the general cooling is quite weak. Nonetheless, again, the contrast changes, and if you have colder waters over the ocean, that means less precipitation over land because you have winds. Winds blowing over colder ocean will bring less moisture onto land. So the regions like Southern Europe, the Mediterranean will get less precipitation. And that's an important thing to keep in mind, especially in the context of general expected drying of the Mediterranean. So a weakening of Emoc would contribute to this drying. Tropical cyclones, well, there will be changes in the tropical cyclones just due to the weakening of Emoc. And this is from a recent paper we are working on with my student Emily Levine. Because the Emoc brings less heat to the northern hemisphere, more heat remains in the southern hemisphere. And so you expect more hurricanes, and these are red boxes. You expect more hurricanes in the Indian Ocean and more hurricanes in the Pacific. Overall, you expect fewer hurricanes or tropical cyclones in the northern hemisphere, in particular in the Pacific. However, if you look in what we project to happen in the Atlantic, there is a very unexpected result. There is a general reduction in the frequency or probability of hurricanes in the North Atlantic. However, there is a shift. There is a shift in the distribution, and the shift is such that you actually expect more hurricanes in this red box. So along the US eastern coast, and in the Gulf of Mexico. And this is quite unexpected. And this is actually in addition to the expected increase in the strength of tropical cyclones. This is index, GPI index, so Genesis potential index. So you can interpret as a frequency of cyclones. And so a weakening of AMOC surprisingly give you more hurricanes for the eastern United States. So to summarize this, there are some good things, but there are some pretty bad things that you expect from a weakened AMOC. One thing that I haven't worked myself on, but a weakening AMOC shifts the tropical Atlantic rain belt, and that would mean less rain for the Sahel. So another impact. All right, so let me continue. And the next part of my talk aims at looking at which factors may actually affect the AMOC slowdown, affect the rate of AMOC slowdown, stabilize it, or speed up the slowdown with global warming. There are many factors. Obviously, the rate of warming is an important one. Potential melting of glaciers is an important one. But here I will look at two particular phenomena that's probably sort of the salient features of global warming. And the first one is the warming of the tropical Indian Ocean. The second one is the Arctic sea ice decline. And for the remaining part of my talk, I will focus on these two phenomena and how they may affect the AMOC. All right, so I'll start first with the warming of the tropical Indian Ocean. If you look at the trends of SST, perhaps the most robust trend is the trend in the tropical Indian Ocean. This red box here, and if you compare this trend, something like 0.5, 0.16 degrees Celsius per decade, it's roughly 50% higher than in the rest of the tropics. So the ocean is warming almost everywhere, but the Indian Ocean is warming faster. This trend, we have pretty good data for the past 80 years, and this is a robust trend, and so the Indian Ocean is warming. If you take 80 years of this trend, we're talking about excessive warming of 1, maybe 1.3 degrees in the Indian Ocean. You probably would be, you would probably not think right away that this would affect the AMOC in the Atlantic, but it turned out to be actually quite a robust way to change the AMOC. But before we go to that, one thing to mention, well, climate models actually do not reproduce this Indian Ocean warming. And this is a trend, actually not a trend, it's actually temperature anomaly for the past 20 years or so. In historical simulations of coupled models, the CMIP6 data set, and you don't see this enhanced Indian Ocean warming. So coupled climate models failed to reproduce this Indian Ocean warming. And that has strong implications on their ability to produce the right rates of decline of AMOC, as hopefully will become clear in a few minutes. All right, so what we did to show the importance of this warming for the AMOC and climate in general, we took a climate model and did a relatively straightforward experiment. We imposed an Indian Ocean warming in this region. and vary the magnitude of it. It was 1 degree, 2 degrees C, and we actually did cooling as well, -1 degrees and so on. And looked at 2 centuries of this perturbed simulations. So the Indian Ocean warming is actually affects the entire globe because it works like a heater. So you add a heater in the tropics, so the entire planet would notice. And so these are temperature changes in the global over the global ocean. So you see warming regions, cooling regions, but mostly it's warming. And then we looked at the AMOC. And so this is the AMOC that I showed you at the very beginning. So this is the control simulation. And then we looked at the strength of AMOC in these perturbed simulations. And these are our results. So as in several decades after we imposed the warming of the Indian Ocean, we had the strengthening of AMOC. And it's pretty robust. The higher warming of the Indian Ocean, we get a stronger AMOC strengthening. For 1 degree, we get something like a 6 Sverdrup increase in the AMOC strength. And this is huge if you're thinking about variability, even the future trends. 1 degree warming of the Indian Ocean imposed really strengthened the AMOC. We also did cooling experiments, and the cooling works in the opposite way. We also repeated these experiments with a different model at Lausanne, and it's very robust. So you can ask whether this can be put in the context of observations. So these are our different different experiments, there is actually a linear dependence of AMOC strength on the warming of the Indian Ocean. And the gray band is sort of a range of the warming of the Indian Ocean you would expect. And so you get something like maybe 3 to 4 Sverdrups of strengthening of AMOC if you take into account this enhanced Indian Ocean warming in this particular model. Okay. The next question you can ask, why would AMOC be strengthening? Well, the major reason is salinity increase in the tropical Atlantic, and then advection of this salinity anomalies to high latitudes. And this is just a map of the salinity anomalies. Why do we have salinity anomalies? Well, when you warm the Indian Ocean, you enhance convection there, and that works like a vacuum cleaner. So it takes more, it accelerates convergence of moisture to the Indian Ocean, to the Western Pacific as well. And on the other hand, it creates a deficit of moisture in the Atlantic. And so you develop salinity anomalies, higher salinity, so less precipitation, high salinity. Both salinity anomalies are advected to high latitudes. And as I said at the beginning, higher salinity, denser waters, so you strengthen the AMOC. And this is just one example. Enhanced Indian Ocean temperature warming, you wouldn't expect to have anything to do with AMOC, but nevertheless, the AMOC turned out to be very sensitive to this enhanced Indian Ocean warming. So, and again, this is not taken into account in climate models because, as I just demonstrated, they don't reproduce this enhanced Indian warming. They just generate a warming in the Indian Ocean, but it's uniform as anywhere in the tropics, in the tropical oceans. So they don't have this effect. All right, so let's continue. Now let's talk about another salient feature of global warming. It's Arctic sea ice decline. And as I will show, it has actually a completely opposite effect on the AMOC. So it's been on the news for quite a while. Well, we're losing permanent sea ice. Sea ice in the Arctic is thinning. The concentration of the Arctic sea ice is getting smaller. Especially it happens in summer. There is a little bit of decline in winter as well. 2012, and this is what you see here, was the smallest extent of summer, actually September sea ice over the satellite era. So the red line, sorry, the yellow line here is climatology, and the white area is sea ice at here. You can look at this from a point of view of ice concentration, and purple color here, it's the loss of concentration of sea ice in the Arctic. Time series showing this robust decline of sea ice, and the purple line here is the observation of the Emoc from the rapid, just to give you some perspective. All right, so how would Arctic sea ice decline affect the Emoc? Well, we conducted somewhat similar experiments, taking the same model, and to isolate the effect of Arctic sea ice decline, we imposed a reduction of sea ice comparable to observed by perturbing radiative imbalance, by creating the radiative imbalance of Arctic sea ice. You can do it by many ways: reducing albedo of sea ice, reducing emissivity of sea ice, changing thermal conductivity of sea ice. We tried all these methods, and they work more or less similar. And so these are the experiments. We started with the control experiments. This is our perturbed experiment, and this is the difference. So we lose sea ice in some generally similar way as in the observations. There are some differences, but in terms of percentage of sea ice reduction, and this is what we call shortwave experiments. So it's reducing the amount of shortwave living sea ice. So we sort of, we reproduce the reduction in sea ice in terms of seasons. So the largest reduction in summer, a little bit of reduction in winter. And so these are these experiments with different amount of Arctic sea ice decline reduction, different experiments. The black line is the control. And as soon as we impose our perturbation, sea ice declines. It takes something like 10 years, maybe 20 years, and then you get a sort of quasi-equilibrium new state with a small amount of sea ice. So these are 4 experiments we did. This is the response of the AMOC. So as soon as we have a reduced Arctic sea ice, the AMOC starts slowing down. And it's proportional to the amount of sea ice decline. So how much AMOC slowdown you expect. So the blue line here is probably the realistic case. So comparable to observation. So in terms of sea ice decline. So if you take the light blue line as our base experiment, we expect something like 3 to 4 Sverdrups decline of Emoc. So you can ask why Arctic sea ice decline would affect the Emoc. Well, because of 2 related mechanisms. You open the area of sea ice, so there is more sunlight going into the ocean, warming the ocean. So you get this warming or in the Arctic and in the subarctic. Warming means less dense water. So that prevents sinking. Plus you get a freshening of the Arctic. And this freshening largely due to the seasonal melting of sea ice. And so this fresh water stays near the surface of the ocean. It creates a lid. So again, less dense water prevents sinking. And so this warming of upper ocean and freshening of the upper ocean work to reduce the strength of Emoc. And this is just an animation showing how pronounced the freshening of the Arctic happens in these simulations. So the blue color here, it's change in salt. So blue means freshening. And this is 200 years of simulations where we reduced the amount of sea ice in the Arctic. The freshening starts in the deep Arctic, and then it spreads to the North Atlantic, to the regions of sinking. In the meantime, salt accumulates in lower latitudes. There is one effect here that amplifies this salinity contrast, so more salt in the tropics, less salt in high latitudes. Well, it's the so-called salt advection feedback. Because the Emoc starts weakening, it brings less salt to high latitudes, and that freshens high latitudes, and in turn that further weakens the Emoc. So there is a positive loop, positive feedback loop that creates this strong freshening between North America and Europe. But its origin, the freshening of the Arctic, and then the signal spreads to the North Atlantic. All right, so I'm almost done with my presentation. So just to summarize these two perturbation experiments, tropical Indian Ocean warming and Arctic sea ice decline. In the first experiment, so tropical Indian Ocean warming, I emphasize the role of salinity. So due to the warming of the Indian Ocean, the Atlantic Ocean becomes more saline, and that tends to stabilize the Emoc. And this I have more diagrams for salinity. So this is latitude, these are years. So a red, orange signal here means high salinity. On the other hand, the freshening of the Arctic leads to a weakening of Emoc, and you can see this reduction in salinity in high latitudes. So we took these two salient features of global warming, conducted with relatively simple experiments, and what we found, they have opposite effect of Emoc, and in particular in our idealized cases, they sort of compensate each other. Obviously, this is just one model, and these effects can work differently in other models. But you can imagine that if there is a mismatch in one of these mechanisms, you can have overly stable Emoc, or you can have Emoc prone to weakening and slow down. And so predicting the future, predicting the rates of Emoc slowdown depends on such things. And these are just two things. There are other things, and there are plus some characteristics of the model, like general stability of ocean circulation that also affects the rates of Emoc's future slowdown. All right, so this is a summary of my talk. And these are some general general conclusions. So I think it's pretty clear that the AMOC is expected to slow down in the 21st century. However, whether it has been already weakening is unclear. There is tentative evidence that it might be weakening. There are other lines of evidence suggesting that, well, not yet. And the North Atlantic warming hole, unfortunately, it's not a reliable indicator for AMOC weakening, as it can simply reflect global warming-induced changes in winds. The future weakening of AMOC will increase the land-sea temperature contrast, which may increase storminess in mid-latitudes, shift tropical cyclogenesis, make the Mediterranean region and Europe in general more arid. Plus, I forgot to mention here the effects on the Sahel. And finally, the rates of AMOC slowdown depends on many local and remote factors. I just showed you examples of the role of enhanced tropical Indian Ocean warming and Arctic sea ice decline that appear to have opposite effects on AMOC. So some of these results has been published in these papers I have for the references. So you are welcome to read them. Several of papers are still at work, but hopefully we'll finish working on them this year. All right, well, thank you very much. That's my talk.
Thank you, Alexey. That was excellent. Yeah, as normal, you can ask questions by raising your hand, putting it in the chat or in the question and answer tool. And I see hands already rising, but as normal, I take the honor of asking the first question. I can easily understand why the Arctic sea ice is declining, but why is the tropical Indian Ocean warming more than other tropical regions?
That's a very good question. And it's a good question for two reasons. One reason is because the climate models cannot reproduce this warming. The second reason is physical. So one of the hypotheses, and we actually, my student Ulla Hidi and I had a recent paper in Nature Climate Change. The ocean in the tropics work as a thermostat. The idea of a thermostat was put forward by Amy Clement, Mark Kane in the 80s. But they looked at this idea of the thermostat as a sort of stationary phenomena. You warm the ocean, you get the thermostat, and that reduces warming. We looked at that as a transient thermostat. And what happens if you think about the Indian Ocean and the Western Pacific, it's dynamically passive regions from the point of view of the ocean. You can think about them just a slab of ocean, mixed layer ocean, that's getting warmer due to radiative effects of global warming. However, the Eastern Equatorial Pacific is a region dominated by upwelling, so it's colder deep waters coming to the surface. It's Central and Eastern Tropical Pacific. There is a similar equatorial upwelling in the Atlantic Ocean. And so in response to radiative forcing, what happens, you can actually strengthen the winds. And you strengthen the winds that strengthen upwelling. So you bring more colder waters to the surface that compensate the warming from above. So radiative effects are balanced by colder waters coming to the surface. It doesn't happen in the Indian Ocean. It doesn't happen in the Western Pacific. So the only way to balance this radiation in the Indian Ocean and the Western Pacific is to raise temperature. In the Central and Eastern Pacific and part of the Atlantic, you can actually increase winds and increase upwelling. And this is what's actually seen in the observations. In the past 40 years, trade winds along the equator has strengthened by something like 20–30%. And so that's a tentative explanation. So this thermostat is a transient phenomenon. As soon as you warm deeper waters, and we're not talking deep waters, but we're talking about the waters at a depth of 100 meters, this effect of cold upwelling is reduced, and then the thermostat effect will disappear. But for the time being, it seems like this thermostat is working. There is another possibility, is the effect of aerosols, spatial differences, anthropogenic aerosols. That might be a factor as well. But my preference explaining this would be to look at this dynamical transient ocean thermostat.
Mm-hmm. So it's mainly
that warming in the central and eastern tropical Pacific.
So that the Indian Ocean doesn't have this strong equatorial system as well.
No. So
okay.
Trade winds are very strong in the Pacific. In the Indian Ocean, actually the winds are reversed and weak compared to the Pacific.
Okay, thanks a lot. That was very interesting. Chen is next. Chen 1.
Yeah. Hi, Alex. Yeah, it's quite interesting you propose these two factors. As an example, I know there's many factors in the ocean and Arctic sea ice loss. So my question, I assume your modeling study is basically the equilibrium type, right? So you have a forcing and force the model about 200 years, and you see the converge response. I was really curious as, when you have so many factors on table, whether the transient response of the Emoc to certain factors would be quite different, or in general, do you, at least hypothesize the transient response might be a lot lower than equilibrium response?
Yeah, that's true for sure. But let me clarify. So we said 200 years old. The experiments are 200 years. But we looked at both the equilibrium response and sort of transient response. So the transient response, in both cases, has similar time scales. We're talking, we start seeing the signal something like in 20 years. And then between 20 and 100 years, there is an adjustment to equilibrium. So somewhat in between 20 years to 100 years, it's comparable what we are doing with observations of sea ice decline. It's the past several decades. Tropical Indian Ocean, the past 70 years, so the trends. So we see exactly the same signal, but maybe like 70% of equilibrium. There is no dramatic differences. If you look, for example, if you go back, if I can go back to the time adjustment, like this is our transient.
Yeah.
So the signal is still there. It's not as strong as the equilibrium, but you reach like 60%. And if you go to the tropical Indian Ocean, again, after 60 years, you get maybe 60% of the signal, maybe a little bit less, maybe 50%. So the direction clearly the same, just you need to wait more until the equilibration of the system happens.
Yeah. Specifically, I know that you mentioned aerosol or something. So these things are very highly transient forcing. Just curious how fast Emoc will be sensitive to certain forcing in the transient sense. But
so we're talking about multi-decade time scale from 20, 50, 60 years. So this is
okay. Yeah. Thank you.
Okay, Alessandra, please.
Hi, thank you. Yeah, thank you, Alexey, for the interesting talk. I have actually a somewhat related question, and that is this. I was intrigued by your discussion of the role of the warming of the tropical Indian Ocean.
Yeah.
And I know you didn't look at this in detail and you said that, but in the historical period, actually the warming of the Indian Ocean is implicated in Sahelian drought. And so this again raises the issue of perhaps different time lags and whether it's transient or equilibrium responses that could lead to drier or wetter Sahel with this role of the Indian Ocean. I thought it was interesting.
Yeah, so thank you. I can comment on this. So we looked at various things. So in the first thing, obviously, you look at the atmospheric response to tropical Indian Ocean. And as you mentioned, the effect on the Sahel is one of the things. You also generate a Rossby wave train going to high latitudes, North Atlantic, changing the NAO pattern there, like imposing a steady positive like NAO pattern there. And then you have an adjustment of the tropical Walker circulation that I was referring during my talk, where you strengthen the Walker circulation in the Pacific and the Atlantic Ocean, and that reduces precipitation over the tropical Atlantic. That happens obviously at very fast time scale. We're talking about weeks to months. This is a fast atmospheric response. The Emoc then responds to density anomalies. And to build a density anomaly, that requires time. And so that's why you get much longer time scales, decadal, multi-decadal time scales. And in case of tropical Indian Ocean, you reduce precipitation when you warm the Indian Ocean. You reduce precipitation over the Atlantic, over the tropical Atlantic. That builds salinity anomalies there. And it takes like 20, 30, 40 years for those salinity anomalies to be advected with the currents to the regions of high latitudes where dense water sinks. And so that's where you get this long time scale. The building up and advecting of density anomalies, in this case due to salinity. And so you get much longer time scales.
Yeah, thank you.
But looking again, as you mentioned, atmospheric response to Indian Ocean warming, you see it almost everywhere. Because I like this analogy of putting a heater. And so you see the effects almost everywhere. And the Indian Ocean tends to be like very important for atmospheric circulation.
Yeah, I mean, the simplest would be you're increasing convection there, you warm up the upper troposphere and then you stabilize. And so, yeah, that has a global effect then. And if it's the Indian Ocean doing it, fine, it could be the Pacific and then at different times.
So what's interesting about the Pacific, if you do it in the Pacific, you miss the North Atlantic. Not completely, but somehow you don't see that effect anymore. We tried to do that the Pacific experiment, and you see some signal in the Atlantic, but it's not as impressive. So somehow the Indian Ocean is a sweet spot for the Emoc.
Yeah, so you're saying there really is something specific about the circulation and this Rossby wave response that's set up from the Indian Ocean.
Yeah, yeah.
Okay, thank you.
Okay, I maybe have a final question. I mean, I know that this mooring work is a lot of work. I am biological oceanographer myself, working on also having now some instruments on moorings at the equator. So how good do you think can you measure the Emoc, this rapid array, and what is the error in these measurements?
I think a good estimate, a good rough estimate would be plus minus 1 Svedro. But some people say it's 10%. So that would be more than 1 Svedro. And part of it is related to the fact what assumptions you make in terms of bottom ocean water. So there are no actual measurements of the flow near the bottom, so it's just an assumption that there should be mass conservation. And so mass conservation does happen, but the time scale of this mass conservation vary. I guess the important thing is the time scales. So you look at the variability, you look at the trends. So the actual accuracy will change. If you look, for example, variability at annual time frame versus decadal. Yeah, but in simple
would you
terms,
say there
I would say accuracy from 1 to 2 Sverdrups.
Would you say there needs to be more measurements or more moorings out to do it more precise?
You know, they actually try to do to go with fewer measurements because it's expensive.
Yeah, I know.
And so what they try actually to remove some of the moorings to see whether they can have the same accuracy with fewer measurements. But I think what's important, this is just one array. We have now more arrays, for example, OSNAP array at higher latitudes and arrays in the southern hemisphere. So rather than increasing accuracy, adding more arrays give you much more information. Yeah, so there are other things like, you know, you need to know wind stress to do the calculations. And wind stress come from reanalysis products. So it's atmospheric models with data simulations. So it's a small component of transport, but it adds some errors. So each element, how you calculate, like there's some error. But again, if you ask person who is more confident, well, he or she would say 1 Sverdrup. Some people say more than that. So